We've already talked quite a bit about statistics in Wireshark, and we've done that through the lens of a lot of things that exist up here in the statistics top level menu. So we've talked about protocol hierarchy, we've talked about conversations and endpoints. We've done a few of those things, and we've maybe not called them statistics or referred to them as statistical features, but that's exactly what they are, which is, of course, why they're under this heading. Now, in this section, I want to go over a few other statistical options that Wireshark provides. And statistics are really important for doing packet analysis for a lot of reasons. The primary reason is that most of the time you're going to be dealing with a lot of packets. Everything in this course is kind of constrained, and we've stripped out all the unnecessary stuff and just given you really tight examples focused on what we're discussing, so we don't have to worry about the extraneous stuff. But in the real world, you are going to have to worry about the extraneous stuff because generally you're going to be doing a packet capture from a machine that may have a lot of other stuff going on. Maybe the user's browsing on it, or there's just a lot of normal broadcast or noise traffic being generated from the machine. And we certainly know that to be the case with, especially with modern Windows operating systems, which seem like they're always chatting around about something. So you're going to have to deal with that. And nonetheless, even if you're not dealing with that, you're probably dealing with packets you've captured from some type of activity, and there's just going to be a lot to deal with. The packet capture I have on the screen here, HTTP ESPN fail, is just one person browsing to ESPN.com. It's not loading correctly, which is why it's a fail. But in this case, we're still getting 569 packets, and that's a lot of packets. That's really more than you can kind of just scroll through to see what's going on. You have to have an ability to understand at a high level some of the things you should look at. Again, analysis is all about asking the right question, but you need some things that help you help point you towards that question. I could ask the question, what's wrong here? But that's too broad, right? I need to get a little more specific. So I need to understand what's going on, look for certain types of anomalies, and try to detect things that can lead me to ask good questions. So that's what statistics are about. And there are several of those offered here. We're not going to go through all of those, but you can see there's a whole lot of things on here. We've gone through conversations and endpoints, but I want to talk about several other of these, particularly some of these that are protocol specific. There are a lot of things, a lot of value to gain here in different situations, so I want to go through a few of these. Now, if you look behind here, you see we have a lot of HTTP packets. So I think the first place to start probably is by looking at the statistics Wireshark offers for HTTP communication. And you can see we have an HTTP option here on the screen. Not every protocol has statistics associated with it. You see there are only actually a few listed, but HTTP is one of those, and it's one of the more common ones you'll use. Some people don't use these at all. I do. I use a couple of them quite a bit, and I'll talk about a couple of the use cases and scenarios of where you can derive value from those. First off, let's just go down this list here. We have three of these. We have packet counter, request, and load distribution. We'll just start at the top, and I want to go through all of these and talk a little bit about the value they provide. Now, in this case, we have the packet counter listed. I've gone ahead and expanded this out to where you can see everything that's going on. And for the most part, you can see this is broken down by the number of packets falling into a certain number of categories. So everything's expanded here. You see we have total HTTP packets, and in this case, there are 14. Of course, there's a lot of traffic here. There's 569 packets, and most of those are related to this HTTP in some way, but they're more the transfer of data from HTTP commands. What this is actually counting is the actual HTTP packets with HTTP headers. So that would be both HTTP requests and HTTP responses. And you can see that broken down a little bit more specifically. We have a section for HTTP response packets, which counts for 7 packets. And then we have HTTP request packets, which are the requests that lead to the response. We have 7 of those. So as you might expect, 7 requests equates to 7 responses. There's an even number of those. If there wasn't an even number of those, that means maybe a request was never responded to, or maybe a response had to be sent twice due to some type of retransmission or something like that. But if those numbers didn't match up, that might be something you'd be interested in looking at. You can actually look at the numbers themselves, or you can go over here and look at the percentage distribution and see that 50% are responses, 50% are requests. Again, things are expanded here, but if we unexpand those, that gets a little easier to see if we collapse those back down. Now, if I expand those back out, we'll look at requests first. And of course, most requests are going to be a GET request. You can have posts and things like that, but most of the time you'll be seeing GET requests. And in this case, all 7 of the requests that were made are indeed GET requests. So we see here that 100% of those are GET requests. I'll collapse that back down, go over to responses, And our responses are a little bit more varied. We have a couple different levels here. We see we don't have anything in the broken range or the server or client error range, 500 and 400 response codes. We do have at least one redirection here, a 301 moved permanently. And then we also see 6 successes, so 200 OKs, and that makes up the array of responses we've gotten here. So looking at this screen is a really great way to look for things that might be amiss. If, say, you're browsing a website and something's not loading correctly, if you have a packet capture, you can go in and look at this and maybe see if you have some 400 or 500 errors. Particularly 500 errors is something you'll see a lot of if there's some type of weird error going on with a web server you're communicating with, whether it's your own and you're trying to get it configured correctly, or whether it's someone else's and you're just wondering why a service isn't working. So this is a really great screen for coming in here and spotting errors. The statistical value of this, it shows percentages and things like that, and that's great. I don't use those as much, but again, if you can look at the distribution of responses to requests and look for a variance in that might find a place where something's going on, and maybe you can ask some questions or dig a little deeper. So you do have the ability to dig in there. Also, of course, you have the ability to go in here and enter display filters to limit this down a little bit and limit the statistics of what you're looking at. But that's Packet Counter. It's a good place to start. I do use it from time to time, and I think you'll find a few use cases where it might be useful for you as well. The next statistic I want to talk about in relation to HTTP is the HTTP request statistic. Now, before I click that, I want to talk a little bit about requests, right? We're going to talk about HTTP in detail more later. But we know that with HTTP, we're requesting data from a web server. So each of those requests is unique, and we're requesting a specific resource. In this case, I'm just requesting get /, which is saying to get the home directory of the web server. But in a lot of cases, I'm going to be requesting, a specific HTML or PHP or whatever page, or a file resource like a JPEG or a PNG. So each one of those requests is something that can be tracked individually, and for the most part, HTTP is always going to request a single entity at a time. So we're going to request one page, then another page, then another page, then a file, then an image, then a video, then so on. Each one of these is going to be separate. So for one thing, that can be really chatty. That is going to be a lot of traffic, especially when you're browsing to a really complex and diverse web page like a news site with a lot of advertising, or maybe something like ESPN here, which has a lot of embedded content. You're going to see a lot of requests. Now, you'll notice we have a request listed here in the info column, so we can actually see that request pretty easily. Now, we can only show those requests here by applying the filter http.request, and it's going to show us there are just a few requests. It looks like 7 requests here in this capture file. So this is a valuable way to look at those, just if you just want to scroll through them, or if you're not looking at a lot of requests you need to go through. But this doesn't provide any statistical value to us, right? I can clearly see there are 2 requests for get /, but if there were 100 requests here and 30 of them were get / /, I wouldn't be able to count those too easily. That wouldn't be the easiest thing to do. So that's where the HTTP request statistic comes in, because it does let us get an overall bigger statistical picture of what's going on. So I can open that by going statistics, HTTP request. Now, when you look at this right off the bat, it's going to look a little deceiving to you. You're going to look at this and say, okay, this isn't any better than applying the filter, because it's only showing me the request and it's not showing me that statistical overview that I wanted to see. Well, bear with me here. There's an interesting thing in that this is actually a table, and what you're looking at here, this topic item area, is actually one column, and it's going to automatically by default expand to the default width of the longest URI here. So if I scroll all the way to the right, you see there is actually statistical data here. So I can go ahead and rein that back in a little bit, and now I actually get the statistics I'm looking for. So we do indeed have that data we can work from, and at that point we can actually see these individual requests. Now, one trick here is that they're organized by host and then URI. So again, it says HTTP request by HTTP host. So the first level is the host. So we have www.espn.com as a host, and then we have espn.go.com as a host. So we see our request for /, which is the same URI, but is not on the same host. So that's actually going to show us 2 requests. We see all of our other requests here. We see one for a JPEG. We see one for some JavaScript here. So we do see those. Now, the trick is here, if there were multiple requests for the same thing on the same host, you would see that. So if there were multiple requests for this JPEG right here, you would see this count incremented. Now, the way modern browsers work, they tend to cache a lot of things, especially images and things like that. So you shouldn't see as many repeated requests for things. That's not something you're going to see as much of in some cases, not in all cases, but especially for like media files and things like that. So when you're looking through this, one thing you can look for potential issues are very large counts of the same request. Could indicate the request is failing. Maybe that resource isn't available, and you can go look at the HTTP response codes to see if there may be some 404s or something like that. Maybe it's something that requires that isn't being cached and requires a request very often, and maybe it's happening too often and taking up too much bandwidth. A lot of different options here, but this does give you an ability to look at those counts as well as look at percentages and distribution of things in relation to other things and get a sense of what's going on. So just another way to look at requests. I generally use this sometimes in conjunction with the filter, the http.request filter. I normally start with the filter so I don't have to pull up this separate window, but sometimes I'll pivot over to the request just to get a nice summary view of what's going on in this view that's request by host, which is a nice way to look at it. And of course, we can apply filters to this as well, same as we could with the other statistics. We only have one more HTTP statistic I want to look at, but it's one of my favorites, and it's the load distribution statistic. Now, it's another one of those where we want to collapse some things down a little bit. So I'm going to make this a little bigger, make it a little wider over here as well. Expand this out just a little bit so it's a little easier to see. And you'll see everything's expanded, and I want to collapse some of those things down. So I'm going to go ahead and do that and show you how this is laid out. Now, what we're looking at here is load distribution, and we're doing that in two ways. One is HTTP responses by server address, and another is HTTP request by server. So these are essentially group bys or aggregations of statistics based upon what's been observed from HTTP data. Starting first, we have HTTP response by server address. So we're going to have an entry for every server address that an HTTP response was received from. In this case, we have 7 of those, and you can see the distribution. So we can see, for instance, all those came from different places, except for this one. So except for 72.246.56.35, 2 responses came from that. So that's responsible for slightly more of the traffic. In this case, we see that's 28.57% of the traffic, at least in terms of the count of packets. Everything else is 14.29%. So important things here. One to keep in mind, this is based upon count of packets and not bandwidth. Packets can be different sizes. You can have really small control packets and you can have really big data packets. So count does not necessarily equate to bandwidth in every case, but something to keep in mind that there is some relationship there, but it's a little bit of a loose one in a lot of cases. So when you're looking at this data, the things you want to look for in terms of looking for problems, look for which host is the top talker. Look for which one is responsible for the majority of the communication, and make sure that's the one that's supposed to be responsible for that. Make sure you're not getting too much data from the wrong place. That's a good place to go. If you're expecting something to be responsible for a lot of the communication and it's not, maybe it's responsible for only a smaller amount of it, pay attention to that too. Now, count doesn't relate to size of the packets fully. So sometimes you may have a count that's really, really high. You may have thousands of packets, thousands of responses from the single server addresses. But those responses might not be OKs. In this case, you see we're all looking at OK responses, HTTP 200 OK, meaning the file was found and is being delivered. However, what if you have 404 not found responses? Well, those will be shown here too, and that's pretty great because then you can look for distributions of those, and a server that might have 10,000 packets responding in a HTTP response, they may actually be 404, so you may be continually trying to retrieve a resource that isn't there. And if it's your server or you're testing your development or something like that, you can go in, fix that, and this is a good way to find that type of error. So a lot of good can come of this by looking at responses by server address. Now, we can also look at requests by server. So these are the requests we're making to the different servers. Again, at this point, we have an entry for every IP address, and then we have an entry for every individual host under here. So we can kind of see which host exists on the same server. So for instance, a1.espncdn.com and a4.espncdn.com, or at least a request being made to the same IP address, the 72.246.56.35. So you can kind of see the distribution of host name to IP address mappings. That's information you can get from DNS data and looking there, but also you can get it here, which I think is a pretty neat way to look at it, and that's HTTP request by server address. You can also flip the script on it a little bit and go HTTP request by HTTP host. So this is the same thing, just flipped. So instead of grouping by IP address and showing the host, here we're grouping by host and showing the IP address. So we can see if a single domain resolves to multiple host address. So just another way of looking at that, which is pretty valuable. So keep in mind when you're analyzing HTTP traffic to dig into these HTTP statistics, because they are really good about giving you an overview of what's going on. You can think, okay, I'm just going to apply some filters. I'm just going to do that and count them manually. Please don't do that. You're going to miss something. It's really easy to look at these lines and miscount or do something wrong and work off of a false assumption. So use the HTTP statistics liberally when you're analyzing HTTP data. We'll be using those in some examples we're going to be looking at later, but I guarantee as you are looking at your own troubleshooting exercises, when you're looking at HTTP data, you'll probably run into a need to use these as well. So be aware of them, learn about the things you can derive and can't derive from them, and you'll be in a much better place. Now, to move on from HTTP statistics, I do want to show you some other stats that are available, in this case specifically related to IPv4. We have those for IPv6 as well. There's no IPv6 in this chapter, in this video, only IPv4, but you'll see they're the same statistics. So everything I'm showing you for IPv4 is also applicable for IPv6 too. Now, I'm not going to show you all these because I think, quite honestly, some of this information is better obtained elsewhere. But I will show you, if we go to this all addresses section, it's going to show us all of the IPv4 addresses that are found in this file, along with a count of the number of packets and as well this RAID and percentage and burst information as well. So now if you're looking at this information, you might say this looks familiar. And if you think that, that's probably because it looks really similar to the IPv4 tab of the endpoints window. So basically all the information you can get from here is also available for the most part from the endpoints statistics window. So in that window also allows you to pivot a lot easier between different layers. So between just addresses or addresses and ports on the transport layer and so on. So because of that, I really don't find myself using this too much, but I did want to show it to you so I could at least explain it and say what it is and why you might want to use the other option. But it is here, and if for some reason you like it, if it works for you, then by all means use it. But I think this information is better obtained from the endpoints window. Now, that doesn't mean that all of the IPv4 statistics down here are useless that are found in other areas. I really do actually like this one, this destination and ports. And it's kind of large, a little unwieldy here. I'll try to make it a little bigger on the screen. But you see it's also giving us some of those group bys or those aggregations that help organize things a little bit better. In this case, we start with every IP address is kind of on this top level. And then we go from IP address to protocol, and then to port. So we're looking at transport protocols here. So we see TCP is one of those. Down here we see some UDP as well, and more UDP down here. So we're looking at basically port per protocol per host, which I do think is an interesting way to break this down. You can almost kind of, it's almost kind of like a protocol hierarchy merged with the endpoints window, and then it shows you the distribution of ports being communicated on in terms of destinations in the capture file. So for instance, for a lot of these hosts you see, for 72.246.56.83, all the communication is port 80 TCP traffic, right? So it's all HTTP traffic. And that's the case for several of these. We can see for 4.2.2.1 here, all the traffic is UDP over port 53. So it's all DNS traffic here. Now, we go down and we see some other things that may be a little more interesting. So for 172.16.16.154, we have a lot more variety. It looks like we have a lot of ports here in the 5700 range UDP, and a lot of them in the 6400 range in TCP. And the reason for this is because this is actually our local host, right? It's our friendly host that's communicating. It's initiating communication out of higher port numbers, so this ephemeral port range above 1024. And these are the source ports it's initiating communication with. So you would see there's actually a correlation between these 7 UDP transactions, and look here, we have 7 UDP transactions for 4.2.2.1. That's because it's our DNS server. So these all represent the initiation of a DNS request, and these represent the response to it. Now, in this case, we're looking at destinations, right? So the packet up here are destined to 4.2.2.1, and these are destined the other way, right? So we're looking at two sides of the conversation here, and this is a really neat way to see it. So in this case, we can see, based upon the high ports and the sequential nature of them, that 172.16.16.154 is initiating a lot of this communication, and a lot of the things up here above it are the servers that are responding. So that's pretty cool. I like being able to display this way and to dig through this. It's a good way to kind of get the lay of the land, dig into specifically into individual hosts, and see what they're doing. Are they initiating communication? Are they responding to it? Is it a client? Is it a server? This window will give you a good overview of whether or not something is a client or a server, and that's pretty darn cool. So there's one more statistic I want to show in this video, which has kind of been a hodgepodge of a lot of the leftover statistics we haven't looked at, but that's okay because there's a lot of good to be found here. I switched to a different packet capture. This one's called download-slow. And I'm going to go here to statistics and go to packet lengths, which is right under conversations and endpoints. Now, when I open this, what it's going to show us is the various distributions of the lengths of packets based upon bytes. So what we're seeing here are all packets between 0 and 19 bytes, 20 and 39 bytes, 40 and 79 bytes, and so on. And you'll see these are kind of clustered around the same area. So we have a lot of packets between 40 and 79 bytes, and then we have a lot of packets between kind of 640 and 2,559 bytes. So we're clustered into two distinct groups, and I think this shows off something very important. Generally, most packets can either be considered loosely as either control packets or data packets. So a control packet is a packet that's used to kind of govern the communication of devices. So these are TCP packets, so like your SYN and SYNAC packets that set up a connection, very small. They're HTTP requests, which are usually pretty small. They're just a small bit of HTTP data on top of TCP and IP data, so nothing too big there. Things of that nature. So all these control packets that make simple requests, respond with statuses, and help set up and control and initiate communication, those are generally pretty small because there's not a large data payload there. And in some case, like TCP control packets, there's no data payload. It's just the TCP data. So they're going to be small. Now, on the flip side, you have data packets, which are going to be quite big because they're going to have, IP data, TCP data, or UDP data, and then they're just going to have a bunch of data. And generally, that data is going to be pretty large in size. I mean, we move a lot of data around, and you're breaking that across multiple packets because you can't fit everything into a single packet, at least not for reliability purposes and as the specs are written. So that's why you see all these large packets here above, most of them above 1,280 bytes, because those are packets that are essentially full. They're 1,514 byte packets or larger in the case of jumbo frames, but they're larger data packets used to send data. So with that said, if you consider that we have control packets and data packets, and you look at the distribution of those, you can kind of start to make some judgments about the nature of a packet capture. Pretty neat. So for this case, this is download-slow. So what we're looking at is a capture file where someone's downloading data and it's going kind of slow, but they're downloading a lot of data. In this case, we see we have 10,000 packets, which is a fair bit. Now, the thing that I noticed for me is that 66% or 2/3 of the packets are very large. So these are pretty much all data transmission packets. And you can actually see here the max value is 1,460, which is the maximum amount of data payload that you can have in a standard TCP or standard Ethernet packet here, right? So that's pretty cool. We can see that these are all data packets, and just by nature of having this many data packets, I can assume there's quite a bit of data being transferred. And because of that, I can kind of assume that maybe there's some type of file download or file request going on. If I were to show you a file where this wasn't going on, you'd probably see a much lower percentage in terms of counts of packets than you would here. You might see something like a 50-50 distribution, which makes sense because every request is often going to have an ACK sent back with it. So 50-50 is going to be more towards smaller communication where not a lot of actual data is being transmitted. If you ever see one of these windows where these smaller packets, these 40 to 79 byte packets, where the majority of packets are in this range, so 70-80%, a lot of times that indicates a problem. It indicates maybe there are a ton of retransmissions, a ton of duplicate ACKs, things we're going to talk about in the latency chapter, maybe a lot of unanswered connections. A port scan, for instance, will have a lot of a higher percentage of control packets like this since no data's being transmitted. So Definitely take a look at this window if you want to get a lay of the land and understand the nature of the packet capture you're looking at. I mentioned earlier, I pretty much always look at protocol hierarchy. I often look at packet links as well because I can quickly glance at the percentage distribution of packet numbers by length and get a sense of what's happening or maybe what I want to do next. So we'll look at this in some practical exercises as we go forward. Now, real quick, before we leave behind this notion of packet links, I did want to show you one example of what I was just talking about in regards to large amounts of control packets. This is a file called synscan.pcapng, and it is actually a port scan. So it's a single device sending one packet at a time to another device across multiple ports, trying to see what port is open. And we'll dissect this specific packet capture later when we go into the security section of the course. But for now, just know that we have one device sending just tons and tons of packets to another recipient device to see what it responds to. Because if it responds to a particular packet, then we know that that port is open and we can maybe try to probe that from a security standpoint or interact with the service there. Now, in this case, we're not sending any data payloads, right? Because we're just sending these TCP send packets. And a send packet, by nature, has no application layer data, or it shouldn't at least. You can see here we're clicked on the first packet, and we have our IP header and our TCP header, but we have nothing else beyond that. Pretty small packet, only 58 bytes in length here. So if I go here to statistics and go to packet links, you can kind of guess what the distribution is probably going to be. All of these packets are between 40 and 79 bytes. Matter of fact, our minimum value is 58 and our maximum value is 60. So they're all right there in the same range. So this is a surefire sign that no data is actually being transferred and you're looking at control packets. You don't see a lot of cases where 100% of the packets are control packets, but a port scan is definitely one of those. But nonetheless, a thing you can look for are high distributions of these control packets and looking for some type of potential problem. With that said, that's pretty much going to do it for this section on protocol-specific statistics. Again, this was just to kind of extend some of our previous discussion on statistics. We've looked at a lot of them with endpoints and conversation and protocol hierarchy. Those kind of deserve their own section. This is kind of a hodgepodge of a bunch of different leftover things that can be useful in the right scenario. So play with these. You know they exist, so when you're interacting with certain protocols, you can kind of play around with them and see what value you can derive. I'm certain you'll find some value, and I tried to impart some of that from my experience on you, but it's going to be really highly situational. We'll look at examples where we pull value from these in different areas. But again, play with them. If you're looking at HTTP, pull up HTTP statistics. If you're looking at just a wide variety of traffic and you want to get the distribution, look at the packet links. That's pretty cool in conjunction with things like protocol hierarchy and so on. So these are definitely things, the more you play with them, the better you're going to get at understanding when to use them. How to use them, not too hard. You just click a button and they show up. Knowing when to use them, that's really the tricky part, and that's the part I want you to get better at.